Culmination of a journey that started in November with the launch of the Mars Curiosity rover, and will begin the science phase the day after tomorrow when it wakes up on the surface and we begin checking it out and begin working on the science of the planet Mars. So what I'm here about today is to give you a little briefing on what that's all about. And I'm hoping it'll be fun. It runs for about 20, 25 minutes, and then we'll take questions for as long as you like. One of the things that the kids should know is that whenever somebody asks a question, they get a reward. So Sherry and Eric have pins, Mars Curiosity pins. Be thinking about a question you might like to ask. And when you ask the question, then we'll give you a pin as well. So let's see. Why do we explore Mars? We explore Mars because when we understand another planet by analog, by comparison, we can begin to understand our own planet. And these are themes. Let's see if this laser pointer works. Not so well. Life, climate, geology, human exploration, those are all themes that help us answer those big questions that we talked about earlier. And the thing that ties them all together is water. Water is fundamental for life. Water is the thing, at least on Earth, that drives our climatology. Water is the thing that helps us understand geology. If you remember your 8th grade science, layering in lake beds and that sort of thing. And water is one of those fundamental things that we seek when we go out to explore. So you follow the water, you begin to get answers. And we have been following the water. The water on Mars has been found. When we landed the Viking landers in the 70s on the surface of Mars, we looked at the place and we said, this is a dry, dusty, arid place. Today we know that that's far from true. What we learned was that just 4 centimeters under the surface of where the Viking landers landed, just 4 centimeters down, if they had gone just a little bit further with their digging, they would have struck a layer of pure water. The water has frozen and precipitated on the poles of the surface of Mars. There's plenty of water on Mars. We just didn't see it when we went there with the Vikings. And so we have been, actually we found it when we went there with the Phoenix lander in 2007. The climatology in the upper right-hand corner of the laser pointer is not working. Those are dust devil tracks that has to do with the motion of climate, with the winds and moving the water around on the surface. There's rover tracks. This didn't expose water. It exposed silicates, which are deposits from water, and alkalis in another geologic layer. But this, in the upper left-hand corner here, is a time sequence image of the same region on Mars. And you see the stripes are changing. What that is the water table warms up in the summertime and begins to drain down that slope. And then over time, it dries out, just like the sand on the seashore when the tide goes out, dries out. And that's what's going on there. Water is seeping out of the surface from the water table down that slope, and then it gets absorbed into the atmosphere, and then it gets redeposited in the cooler spots on Mars, which is up near the poles. We've been exploring Mars for some time. I mentioned Viking in 1970s, but we've also had Mars Odyssey and the Spirit and Opportunity rovers. Spirit is now dead, unfortunately, but Opportunity is still kicking. Remember, the Opportunity rover was designed to last 90 days, and it's been going something like 7 years now. So, a little engine that could. Then there's orbital missions like the Mars Express mission from the European Space Agency and the Mars Reconnaissance Orbiter, which has taken these amazing high-res images of the Martian surface. And Phoenix is a lander near one of the poles that I mentioned earlier. But our biggest mission, boldest mission ever, is the Mars Science Laboratory, the Curiosity rover. It carries a payload of over 100 kilograms of scientific instruments that any geologist or astrobiologist would be proud to have in their own laboratory on the surface of the Earth. So we're taking the lab to Mars rather than trying to bring the Mars to Earth. So we send spectrometers, X-ray spectrometers, mass chromatographs. We've sent drills and lasers and all that kind of stuff. This thing is chock full of scientific instrumentation so that we can begin to understand the history of Mars and look into its habitability. And then in 2013, we'll launch a climate mission called MAVEN, which will look at the interaction between Mars and the solar winds. So, Mars Curiosity rover, aptly named Curiosity by a young school student several years ago, her name is Clara Ma, is all about learning. We're learning about the history of Mars, and in a way, we're learning about our own history. Here's how it came together. This is a rover, has 6 wheels, dual bogie design. It has it's as big as a Mini Cooper. Anybody know what a Mini Cooper is? It's a little car. The previous rovers were about the size of a golf cart. And the one before that, the Pathfinder, which we call Sojourner, was about the size of a kid's toy. So you can get a sense that we're getting bigger and bigger and bigger. This thing weighs about a ton, 900 kilograms or so. In the back, like sticking off the end there, here we go. I don't know if you can see that or not, is a nuclear power supply. The previous rovers ran on sunlight. This one has a power supply very much like Voyager has on board that keeps it warm at night and produces power during the day. Well, it actually produces power all the time. And then the power goes into a battery, and then when we need extra power, we draw down the battery. So, the rover was put together by technicians in these clean room suits. The reason they're in clean room suits is to protect the rover from getting any kind of human contaminants on it, especially things like our own organic matter, like DNA. Because it would be a real bummer to go all the way to Mars, detect some DNA, think we'd found the indications of life, and turn out to be our own selves. So you can see the wheels are covered over. Those covers got removed before launch, and the technicians take great pains to keep the thing clean. And then, once the rover is assembled, they lowered a descent stage on top of it. And those two things are so intimately married that you can't see where the descent stage stops and the rover starts. But right here in the forefront is one of the rover wheels, and there's the rocket engines that you saw in the previous picture. This happens to be, this big foil-looking thing here happens to be the radar for the descent stage. Once that's done, they put the whole thing in a back shell. This back shell protects it during the cruise phase, keeps it warm, and also holds this big canister that has a mortar-fired parachute. It's the largest supersonic parachute that's ever been made. It's 51 feet across. And they use, I believe it's 100 pounds of gunpowder to fire it out of the mortar. So there it is, tucked up inside the back shell. An automobile, a rocket descent stage, a parachute. To keep it from being destroyed by the rush of the Martian atmosphere as we enter, we put a heat shield in underneath it. So there's the stack, the heat shield, the rover inside, the descent stage up in here, the mortar-fired parachute is in the center of this back shell. And then this is a piece I haven't mentioned at all. It's called the cruise phase. It's a whole satellite in itself. It's the thing that keeps the whole stack on course from the time we launch to the time just about 10 minutes before we hit the Martian atmosphere. So that's the stack that goes in the rocket. And then we got the biggest rocket we could afford, and we put a fairing around the whole stack. This is the inside of an Atlas V fairing that protected the stack as we ascended through the atmosphere on November 26, 2011. 8.5 months ago or so, we took off from Cape Canaveral here, and we've been cruising towards Mars ever since with just a little bit of trajectory corrections, no major anomalies, and we are now ready to enter the Martian atmosphere. This is a heart-stopping event. We go from 13,000 miles per hour to 0 in just 7 minutes. It's an amazing sequence, and I'll show you a little bit more about it later. Who remembers how we landed the Spirit and Opportunity rovers? You remember that? Remember we used airbags, the big airbags, and they landed and they bounced and they rolled, and once they hit the surface and they stopped rolling, they sat upright and the airbags deflated and the rovers could roll off. Well, that had an error ellipse, a landing zone, like this big black circle here. That's too big to get down inside Gale Crater, which is where the scientists felt we needed to go to understand the history of Mars, based on what we know now. So the challenge to the engineers was to land inside this red ellipse. That's how big a deal this is. That's why Mars Science Laboratory goes through all the things you're about to see in order to reduce the error associated with the landing so we could get down inside this crater. And it's a deep crater. The peak in the middle of this crater is 3 miles tall. The depth of the Grand Canyon is just 1 mile. So that's how deep we're going. This is a map of the other places we've been to on Mars. And here's Gale Crater, roughly equatorial. And very, well, sort of near, in the vicinity of where Spirit is finally stuck in the mud. So. All right, what are we going to do when we get there? Well, there's a lot of stuff down inside of Gale Crater to look at. One of the most important things is the stratified rock. And where is that? I saw it on here somewhere. Anyway, here's the layered rock right in here. In that region, we'll be able to look at the various layers of the rock inside of Gale Crater, much the same way a geologist on the Earth would go through layers of rock in a canyon or a crater on the Earth. And that would tell us about the history of the Earth during that time frame when it was all formed. The other thing that it'll do is it'll look at clays. The reason that clays are important is because life tends to like to stick to clay. And so if there's any chance that there were ever microbes or algae on the surface of Mars, it's probably buried in this ancient clay. And so we'll go to the clays and we'll take a look at it. So here's a video on how you get to Mars. Remember we launched it.
How do you get to Mars? If you want to send a spacecraft all the way to Mars, first you'll need a fast rocket to escape the pull of Earth's gravity. The heavier your spacecraft, the more powerful your rocket needs to be to lift off. Next, make sure you launch at the right time. Mars and Earth orbit the Sun at different speeds and distances. Sometimes they're really far apart, and other times they come closer together. About every 2 years, the two planets are in perfect positions to get to Mars with the least amount of rocket fuel. That's important. The total trip is over 300 million miles. Finally, make sure your aim is right. You can't shoot for where Mars is at launch time. You have to aim for where it will be when you get there. It's a lot like how a quarterback passes a football. Also, you may need a few thrusts to correct your direction along the way so you don't miss Mars. If all goes well, you'll get to the red planet in about 7 or 8 months. Then, if you actually want to land on Mars, well, that's a whole other challenge.
And so I'm proud to say that we've gotten to Mars. We have met the challenge. We launched at the right time with the right rocket, and we made the correct trajectory correction maneuvers. And now we go through the scariest part. Hoping, praying that all of these systems that we've tested and checked out and double-checked out work properly. And this is how it's going to happen. This is how it'll play out.
When people look at it, it looks crazy. That's a very natural thing.